Hey everybody, I wanted to just really quickly go over some things that I think will be helpful for your homework. We talked about them a little bit in the lectures this week, or Professor Olson talked about them a little bit in the lectures this week, but they didn't really get covered that extensively, and I think they'll be helpful for your homework. First thing, so we've been talking about kinematics, something like particle starts out at a position x initial, xi, at time ti, and then finishes up at x final at time t final. That kind of thing. We're strictly limiting ourselves to one-dimensional motion. So if we consider that kind of thing, that kind of motion, we can talk about three different vector quantities that are important. Okay, displacement, velocity, and acceleration. Now, vector quantities always have a magnitude and a direction. So when I tell you the displacement of the particle, I'm going to tell you how to get from x initial to x final. Okay, I can't just tell you how far away x final is. I can't just tell you if you're standing at x initial, go 5 meters. I have to tell you which direction to go as well. So I need to say go 5 meters to the right, or go 5 meters north, or go 5 meters that way, that kind of thing. That's what makes a displacement a vector quantity. Another thing to point out is that displacement depends only on the endpoints, the starting position and the final position, and it doesn't depend at all on the path taken between those 2 points. So over here I've drawn a number line, right? If I have something that starts out here and it moves over towards x final and then backtracks a little bit and kind of, makes its way around in a circle and then finally gets to x final, its displacement vector is going to be exactly the same. The displacement vector, if I were to draw it, would go just like that. And it's not going to depend on the particular path taken between those 2 points. That actually, so that the length of that arrow that I just drew in there is that graphical representation of a vector has a meaningful length and direction to it that we'll talk more about that next week once we get into two-dimensional motion. Okay, next thing, average velocity. So velocity is a change in position over a change in time, right? The rate at which position is changing is your velocity. It is, since it is defined in terms of a vector, it is also another vector, right? It's defined in terms of displacement. And there's also average acceleration, which is the change in velocity over the change in time. So the rate at which position changes is velocity. The rate at which velocity changes is acceleration. And that has implications for the way to relate different kinematic plots as well. So plots or graphs of position, velocity, and acceleration versus time are often helpful for understanding the motion of objects as they move. And it's really important that you're able to interpret these graphs, to look at them and to be able to say, here's the point at which it's stopped, here's the point at which it's accelerating, here's the point at which its acceleration is maximum, that kind of thing. Just very quickly, we did talk about in some of the videos, for example, about how if your position versus time curve, say, looks like this straight line that I'm drawing here in blue, then that would mean, right, if it's a straight line, then its slope is constant in time, right? A straight line has a slope that is fixed. It doesn't change. So the velocity versus time curve would look pretty boring, right? It would just be a flat line, right? This is an object moving at constant velocity. All right, now let's get rid of those. Now, if I were to draw a velocity curve, right, that also is a sloping line, then of course the acceleration curve, which is the slope of the velocity curve, would be a flat line, right? Because that slope of velocity versus time is not changing in time, right? And the way that something that we didn't talk about is the way to translate from a position versus time curve all the way to an acceleration versus time curve. So if you just look over at the green lines that I've already drawn here, you'll see that I drew something, a position versus time curve that looks something like a parabola. It's supposed to look like a parabola, at least. And the thing to note about this is that the slope of that position versus time curve is changing as time goes on, right? So at this starting point over here on the left, you see it has a negative slope. That means that the velocity is negative at that point. Right, right here, it starts to turn back up. We've now reached the lowest position point, and at that point, the velocity is 0. And over here, we've reached a point where the slope of the position versus time curve is positive, and that's where we have a velocity that's positive. Right now, if you trace it back over here, right, we've gone from 0, right, then we went down to this negative, and now we're back up at a positive velocity there. So this is what it looks like when you have a quadratic position versus time curve. Now, what would the acceleration curve look like? Right, it's this flat line here. So when position is changing with as like the time squared, then acceleration is constant. Now, that means that the acceleration is the concavity of the position versus time curve. So when you consider any curve, the slope of that curve is the concavity of that curve. Okay, so let me just say that again. Think of a curve. Okay, think of the plot of the slope of that curve versus time. Now think of the plot of the slope of that curve versus time. That is a plot of the concavity versus time. Okay, so just really quick, if I had, say, two different parabolas, one with a very sharp concavity and one with a very wide concavity, okay, both of these would give me something positive in acceleration, but of course the blue one would be a lot smaller, right? The concavity there is much less intense, whereas the green one would be a lot larger, right? Because there's a greater concavity to that green parabola that I drew. And if I were to throw another one in here, let's say a red one that's sloping downwards, right, it would have a negative acceleration because it's now concave down. And the overall height of these parabolas in the position versus time curve wouldn't really matter. It doesn't matter if you take this curve and move the green curve way up at a different position, right? The acceleration is going to be exactly the same. Okay, so that's a bit about average quantities. Let's talk a bit about instantaneous quantities. Okay, just conceptually, because we're not going to talk about calculus quite yet. Those of you who are in Calc 1, you're just talking about limits right now, so we're going to hold off on this calculus-heavy kind of thing until later. But you should note that very often we are talking about velocities that are instantaneous, right? There's a conceptual link between that average velocity and an instantaneous velocity, and that's just that we're taking the change in position over change in time in this very limiting case where that change in time, that time step, is squished down to 0, okay? And the same thing for taking the limit of the velocity as that changes in time. As long as you squish down your time step to a very small, right down to an infinitesimally small change in time, that gives you then the rate of change at that exact instant, right? That would be the slope at that particular time, not within some average window of time. So make sure you just understand that conceptual link for now. And just note that whenever you see v of t written like that, right? V is a function of time, then you're always referencing a velocity at that exact time t, right? That's not an average quantity. That's an instantaneous velocity. All right, let's wrap this up really quick. So just a bit about reference frames. So a reference frame is anything that you can attach a coordinate system to, okay? Let's just consider two reference frames in a specific example here, okay? R1, which is going to be the reference frame of some passenger on a train, and R2 over here is reference frame of somebody who's sitting outside of the train, off of the tracks, looking at the train. So obviously these are different reference frames because they come with different coordinate systems, right? If they are both observing the same physical phenomena happening, let's say some guy playing baseball throws a baseball up towards the front of the train, then they're going to describe this differently. They're going to measure different velocities because one of them is going to be at rest with respect to that guy who was throwing the ball, and the other one is not at rest with respect to that guy, right? He's sitting at rest relative to the train track. He's watching the train go by. So from the point of view of the guy in R2, right, the velocity of that ball is going to be the velocity of the ball within the train plus the velocity of the train, right? And from the point of view of the guy who's moving within the train, the velocity of the ball is just going to be the velocity of the ball with respect to the train. So in R1, the velocity of the ball is going to be 70 miles an hour. We're saying the ball's thrown at 70 miles an hour towards the front of the train. From the point of view of R2, the ball will be traveling at 70 miles an hour plus the 80 mile an hour speed of the train, right? So it's 150 miles an hour overall, okay? This reference frame concept is not that complicated in one dimension. It's going to get more important in next week when we get to 2 and 3 dimensions. Okay, so just in general, the velocity of some, say, object in reference frame R2 is going to be the velocity of that object in the reference frame R1 plus the relative velocity between the two reference frames. It's important to consider the vector nature of the velocity here, so that's why I've included the arrows over the top of these quantities. Just consider if the ball had been thrown in the opposite direction, right, then the ball's velocity with respect to the train would be different. It would be negative 70 miles an hour because it would be going in the opposite direction of the train, right? And then in R2, the ball would be traveling not 150 miles an hour, but 10 miles an hour because the 80 mile an hour speed of the train is offset by the 70 mile an hour velocity of the ball going against the direction of the train. And this type of thing just highlights how important it is to keep the direction in mind, keep in mind the direction of the velocity as well as the magnitude. Finally, just want to say something quick about the kinematic equations at constant acceleration, or the KECA. So these are important. We use them a lot, but we can only use them when acceleration is constant. And this is something you really need to keep in mind because chances are, if you have taken a physics course before, it probably wasn't a calculus-based physics class, and in a non-calculus-based physics class, you only handle cases where acceleration is constant, and therefore these equations always apply. But this is a calculus-based physics class, so we will be dealing with situations where acceleration is not constant, where acceleration changes in time. And when that happens, you cannot use these equations. It's a really important thing to keep in mind. So I'm not going to derive the equations for you. I'm just going to talk about them for a second. If you want a derivation, you can go to this video right there. I did it in a lecture last quarter, so it's there and it's available for you. Basically, the way that these work is, so these are the 3 equations that'll be most useful for you. And if you need something, if you're asked for something that's an average velocity, there's an equation that's useful there as well. The way that these play out when you're solving problems is essentially you're going to pick up information from the statement of the problem, and you're going to have to match up where that given information goes into the different equations here. And then you're going to pick one of the equations that has an unknown quantity that you're asked to find. And then you're going to find that quantity in terms of those given ones. And sometimes you need to use multiple equations at a time. Sometimes you need to kind of get creative in the way that you think about your coordinate system So for example, there's a problem on your homework that involves two rocks being thrown up at a different time. And you're going to have to be very careful in the way that you treat your coordinate system in that particular problem. It's probably the hardest problem on your homework. And the reason why is because you need to make sure that your time coordinate is the same when you're using these equations for the two different rocks. So think hard about that on your homework. All right. Have a nice weekend, everyone. See you later.